This conference will now be recorded.
Hi, my name is Julie Morey. I am going to help you hopefully get through some of the practice questions from Module 4, the Unit 3.0 practice questions. And with this module, or this presentation, you'll be able to go back if you need to have some go through the explanation a bit more deeply. You can return to any explanations or go forward. Anyways, so the idea was to use some of the example questions and hopefully run through them in a way so that it allows you to touch on some of the more challenging concepts. But before we get into that, I just want to give you a bit of background into the topic of this unit, which is data analysis interpretation, why we do it, and principles. And then we'll cover like those more difficult concepts through the practice questions and with some more thought-provoking questions. So the objective of this unit is data analysis and interpretation, and the reason why we do this is to provide quantitative evidence for why there may be a problem in your setting or not, and or if an intervention that has been applied has worked or not. And you'll understand that more as we get further along. And before we go jumping into this, because data analysis can be sometimes used in ways that are a little bit questionable. Let's just go into this without saying that you never lie about what the evidence says, and if you're unsure, ask a colleague or an epidemiologist or a statistician, because I know it's sometimes confusing and you want the data to say one thing and maybe it doesn't, but yeah, always go with what your results show you. So one of the first topics in data analysis that we talk about is central tendency, and this typically has to do with data that is continuous. So goes from in equal intervals from one value to the next. So question 4 asks, if the data you're summarizing is very skewed, which measure of central tendency is better to describe these data, the mean or the median, and then explain why? So a mean, or otherwise known as an average, of a skewed data set will misrepresent the data. And the reason for that is if you look at the data and how they are distributed, meaning what are the values across your data set, the mean or the average of that data set is actually being pulled away from the true center of the data, which is the median. And the extent to which the mean is pulled from the median depends on how far away the extreme values are and how many they are. And I always tell students, whenever you've got a bunch of continuous data, always do a histogram. They're very revealing. You can also tell just by visualizing that you've got skewed data or not. However, if your audience that you're reporting to isn't familiar with what a median is, you can provide both the mean or average and the median, and then if you can see a difference between the mean and median, you can tell that there's a skew to your data. Okay, another question, question 7. On your 5-bed surgical unit, the length of stay of patients who are admitted in 1 month were as follows. So these are all days, 1, 2, 2, etc. I'm not going to read them all out, but calculate the following measures for the length of stay for the month. The mean, rounded down to 1 decimal, the median, and the minimum and the maximum. I'm not going to tell you what the minimum and maximum is because you should be able to figure that out. But the mean, to get the mean is just the same thing as an average. So you sum all your values, you take it in your calculator and you punch them all in. And then you count the number of values and you divide the sum by the number of values, which is also referred to as n. And then you round down to 1 decimal place. So the sum is 63, the n is 11. So I divided 63 by 11 and got 5.7272, repeating. And then the answer rounded to 1 decimal place is 5.7. So if it says 1 decimal place, it would be 5.7. If it was 2, it would be 5.73. But typically throughout this course, we'll be asking to round to 1 decimal place, and that's usually sufficient. Now the median, what you're going to do is count how many values, and we know we counted already, there's 11. Then you sort the values, and because I've already laid out these numbers in numerical order, you would find the 6th value, because the 6th value is in the middle of 11. And there you go. So your median is 3. And you can do this with any series of numbers that are continuous, and you're able to calculate the median. And you can see here that the median is 3 and the mean is 5.7. So they're not 100% the same. They are a little bit skewed. Okay, so I've got a couple questions here about incidence and prevalence, because this is most commonly used calculation for ICPs and IPAC programs. So question 8 is, Hospital A has 1,350 patient days during 1 month. During the month of March 2015, there was 2 new healthcare associated VRE cases and 2 previously identified VRE cases in the hospital. And on the 15th day of the month, swabs were taken from all 14 patients on the hospital's ICU, and these were tested for VRE. There were 2 swabs that were positive. So the question is 2 parts. First, calculate the incidence, and the second part is calculate the prevalence from this information, leaving your answer at 1 decimal place. And it's important when you present the answer, make sure that it's labeled correctly in terms of saying exactly what it is that you've calculated. So for the first part, the incidence, the clue amongst this whole cloud of data is that you're looking at the new cases. So incidence will always involve new cases, and it should always involve time in the denominator. So patient days would be your time exposure. So here we have 2 new cases and 1,350 patient days, which describes the patient time at risk. And we can present the final result in different ways. It depends really upon what the convention is or your reporting requirement. Anyways, regardless, the incidence is mathematically 2 new cases over 1,350 patient days. And that comes out to a really ugly number there, 0.000222 cases for every patient day. Now, you can simply multiply this by 1,000 and then convert it to a rate per 1,000 patient days. Or if the convention in your facility is to report it as per 10,000 patient days, then you simply multiply that ugly number there with all the zeros in it by 10,000 to get a rate of per 10,000 patient days. So the answer is the VRE incidence in Hospital A in March 2015 was 2.2 per 10,000 or 1,000 patient days, or 22.2 per 10,000 patient days. So the second part of the question is the prevalence. And so on the 15th day, there were swabs taken from all 14 patients, and these are tested for VRE, and 2 were positive. So your numerator is 2, your denominator is 14. And you can think of prevalence as being a snapshot of the proportion of patients who are positive on the day that the snapshot's taken. So your prevalence is 2 divided by 14 equals 0.0143 for every patient. And because prevalence is often described as a percent, so that means per 100, so you can convert the 0.0143 to a percent by just multiplying the 0.0143 by 100. And please make sure that you add the percent sign. That's a common error that students will make. So the answer for the prevalence part of this question was the VRE prevalence in Hospital A's ICU on March 15th was 14.3%. Okay, graphing. So there's some questions that students will have about graphing because they're not too sure which is the appropriate graph for which situation. And it does kind of make sense once you get the hang of it. And it does make a difference as you're presenting information to make sure that you've got the right type of graph. So in this example, Alex has monthly chlamydia counts gathered for his province over the past 5 years from across 10 regions within the province. Should he present the count data by region using a line graph or a bar graph? That's the first part of the question. And then if he wants to show how often the monthly counts were outliers, and by outliers, this is meaning much higher than normal compared to the other months, can he show this with a histogram? So the first part, which is asking about line graph or bar graph. So line graphs are always for showing trends in the y-axis, which is the vertical axis, that data with increasing values in the x-axis, which is the horizontal axis. The x-axis of a line graph can be any type of continuous data, but the x-axis in a line graph is not an ordinal or nominal data. So whatever you have plotted across the x-axis should be continuous for a line graph. So because he's got regions, he's got 10 regions, regions are really nominal. There's nothing ordered about them. You could sort them by size or alphabetically, but it still would not be continuous. So bar graphs would not be, bar graphs would be the appropriate choice in this situation because he's got nominal data in the x-axis. And then the second part of the question, if you wanted to be looking for outliers, does a histogram work? Yeah, exactly. Histograms will show you how often counts were outliers compared to other months. So on the y-axis, you would have the frequency. And this is one thing that kind of confuses students a bit about the histogram. The histogram on the y-axis always, always, always has the frequency of the counts that you've got across the x-axis. And I'll show you an example. And you could do some more advanced graphing methods to identify statistical outliers, but a histogram is surely a good starting point. So this is the graphing example for the first part of that previous question. So you've got 10 different regions, and you've got counts for each of the regions. So the bar graph is a really good way to, and I made these up obviously because that would be uncanny to have S's across all the regions of the province. And then this is a histogram example. So across the x-axis is values of counts, and in your statistical package or your SPSS or your Excel will ask you when you're making a histogram what the values of your bins are. And for this particular example, I just made my bins every 2. So the first column actually represents 0 and 1, and then the next one goes from 1 to 2, and the next one, etc. And that way it kind of makes it a little bit simpler to read You could also break this up into individual counts so that you would see a bar for 0, a bar for 1, a bar for 2, a bar for 3. But the key is on the left-hand side, on the vertical axis, is the frequency, because this is a histogram. It's telling you how many times in this population, in this population's monthly data counts, chlamydia counts, how many times there was 0 or 1. There was 10, according to this bar graph, this histogram. And then, then you'd read over to the next bar. So the number of times or number of months in which the region's chlamydia counts were 1 to 2, you can kind of eyeball it there, was actually 15, and so on. But the point is that you can, from this question, is that you can identify that there was an outlier. There was 1 month in one region where the counts were either 11 or 12, and there was 1, and it kind of will sit off to the side. And so that's just one way of visualizing an outlier. Okay, now getting into a more challenging area that students sometimes get a bit confused about. We'll go through this kind of step by step, so hopefully this will help. So question 4, Anne has an Excel spreadsheet with columns of data collected on one group of patients, and the headings in the columns are listed below. Identify the data type in each of these columns. So the number of previous inpatient visits in the past 2 years for each of the patients in that group. Then the latest, well, actually, what we'll do is we'll go through them one at a time. So the number of inpatient visits in the past 2 years, obviously is continuous. It's going to go from 0 up to, it could potentially go up to infinity. Oh, that would be a really bad situation. But you get the point that they are, and that the difference between 0 and 1 and 1 and 2 is recognize that there's always an equal interval. So that's continuous. Latest O2 saturation readings, again, those would also be continuous. You'll notice that these could be decimals, they could be integers, but as long as the intervals are the same between each value in a series, then they can be considered to be continuous. Age category, while years would be continuous, if you've got child, adult, or senior, that would be ordinal. And the reason why it's called ordinal and not continuous is because we don't really know, and it's kind of arbitrary as to how you define the cutoffs for these age categories. So these are ordinal. Smoking history, generally we would consider this to be ordinal, but in some instances people might consider them to be not ordered, so not ordinal, but rather nominal. Current hospital unit or ward amongst 5 possible wards, that would be nominal because there's nothing ordered about the wards. They are what they are, and they're all independent. And presence or absence of a catheter. So that would be yes or no. And so then this is called binomial data or categorical data. It could also be referred to as dichotomous because there are 2 potential values, either presence or absence. And then the second part of the question is to test the hypothesis that patients with catheters have more inpatient visits in the past than those without a catheter. What kind of test would you use? So because you've got binomial, so 2 values possible for presence or absence of a catheter, you can test those kind of subgroups of your group of patients and look at the inpatient visits, which are continuous, and to see if the mean of the inpatient visits for patients with catheter is significantly different than the mean of inpatient visits amongst patients without a catheter. And so that's what a student's t-test can do for you. Now, what if you wanted to test if there was a correlation between the number of inpatient visits and the O2 sats? I'm not too sure why you would want to do this or whatever your rationale would be, but let's say that you have been asked to do this. So you've got number of inpatient visits in the past 2 years, which is continuous, and you've got O2 sats, which are also continuous. So the primary ways in which you would go about testing if there was a correlation is to use either a correlation test or a linear regression. Correlation is available to you on any Excel package, and linear regression is available in other more advanced packages. But yeah, so that's how we would go about doing things like that. Okay, now we're going to dive into some questions about odds ratio and risk ratio. So question 17, below is a table of data collected by an environmental health officer following a survey that she's conducted on conference attendees following an outbreak of GI illness. And then the question says, calculate the risk ratio and odds ratio for the illness amongst the attendees who ate chicken salad. So in this table, the potential exposure that they're investigating is the chicken salad. So they've got rows of data that dichotomize the patient or the population into those who have eaten the chicken salad and those who did not eat the chicken salad. And then the columns are dichotomized into cases or non-cases. So actually I'm doing this backwards, but for the odds ratio, you only need to have what are kind of informally known as the inside values. So the odds ratio, you would take the number of cases who ate chicken salad over the number of cases who did not eat chicken salad, and then you divide that by the ratio of the non-cases who ate chicken salad over the non-cases who did not eat chicken salad. It's a bit of a mouthful, but essentially you'll come out to 18 over 10 over 86 over 152, and then you come out to a value rounded to 1 decimal place of 3.2. So the odds ratio in some ways is a little bit easier than the risk ratio because, as I said, you only need to use the inside values. But in terms of understanding the theory of measuring or estimating risk, the risk ratio is actually kind of more intuitive because you think, well, that odds ratio, that looks kind of arbitrary. But the risk ratio is a little bit more intuitive. So you need the exposed and non-exposed totals. So the exposed, or those who ate chicken salad, would be 18 plus 86 equals 104. And then those were non-exposed, 10 plus 152 equals 162. Then the risk ratio is the number of cases out of those who ate chicken salad, so 18 over 104, over the number of cases amongst those who did not eat chicken salad. So 10, or the proportion I should say, but 10 over 162 is the bottom part of that fraction. So it ends up being 0.173 over 0.062, and that comes to 2.8. And I know it's a bit complicated, but if you can try to remember that in terms of how the table is structured, you're less likely to come out with errors. And just so you can get into the habit of laying your tables out where you've got your case and non-cases in your columns and then the exposures in your rows. But quite frankly, even if you accidentally switch them, as long as you logically work through what the values represent, you actually won't make a mistake. It'll come out to the same thing. Okay, now confidence intervals and using them to interpret. So question 11. Below is a table of surgical site infection rates describing data from an orthopedic surgery service at one hospital. Briefly summarize or interpret the data in a way that would be informative to the operating room manager and head surgeon. So in this table, you've got on the left-hand side, their stratification variable. So wound class, ASA score, which is a measure of the patient's inherent health status at time of surgery or before surgery, and whether or not the surgery involved an implant of some kind. Then the next column, the second column, breaks up those stratification variables into the categories. So for wound class, we've got either clean or clean contaminated. So surgeries that were categorized as clean or clean contaminated. And then for ASA, the patients are categorized as being either ASA 1 or 2, so those are relatively healthy people, and then ASA 3 to 5 are the patients that are have more serious health conditions going into the surgery. And then the category for implants would be either yes or no. Then the next column to that is the SSI rate, surgical site infection rate, for those categories. And then beside that is the lower value of the 95% confidence interval, followed by the upper value. So the lower value is always smaller than the rate, and the upper value is always higher than the rate. And you can think of them as kind of being brackets that sit around the rate. And they generally should be pretty much centered around the rate. So the difference between the lower and the rate should be the same as the rate and the upper. Okay, so back to the question. So we can use this type of data when it has the 95% confidence intervals. We can use this data to see if there was a statistically significant difference between the categories by looking at whether or not they overlap. So let's take, for example, wound class. So there's two categories, and the clean has a confidence interval that goes from 0.9 to 1.3. Clean contaminated surgeries have a rate that starts at 1.2 and goes up to 1.8. So if you think of these numbers kind of on a continuous number line, you can see that the upper value of clean and the lower value of clean contaminated actually do overlap. So the two confidence intervals for clean and clean contaminated actually do overlap a tiny bit, just from 1.2 to 1.3. So those are not statistically different. However, when you look at the ASA, the patients in categories 1 to 2, their rate is 0.8. Their lower, the confidence interval around 0.8 is 0.7 to 0.9. And then for the patients in category 3 to 5, ASA scores 3 to 5, their SSI rate is 1.6. The confidence interval around that 1.6 goes from 1.0 to 2.2. And in this case, because 0.9 is actually smaller than 1.0, we can say that the SSI rates in these two categories is statistically different. where the rate for the patients in ASA group category 3 to 5 is roughly 2 times the rate of any of other surgical patients. So the rate for the ASA 3 to 5 category was 1.6, which is numerically twice as high as 0.8, which was the SSI rate for the more healthy patients in the ASA 1 to 2 category. So that's how confidence intervals can be used to interpret data. Now, having said that, the clinical leaders, like your operating room managers and your head surgeons, but also want to know not just about your significant differences, but they also want to know if you've identified any infection control issues and what could be done to deal with these things. And so, yes, it's the statistical information is a tool. It is evidence, and again, as I mentioned in the first slide, you always have to present that evidence as it is, because it is what the data is showing you. And yeah, so it's a pretty powerful tool, because you cannot, they could not then come back and argue to you that, no, in fact, I'm sure that's not the that's not the fault of the patients. It's like, well, actually, it's not the fault of the patients, but that ASA score is a significant risk factor for surgical site infection, according to this data. Okay, now here's a little bit more fun example about odds ratios and confidence intervals. So question 2, Sue is asked to investigate a cluster of GI illness within 2 days amongst 5 children in an elementary school. All the cases were from the same classroom, which has 22 students. She's told that all 5 of the case students attended a school assembly with 120 other students in the school. And during the assembly, everyone was asked to shake hands with everybody else. Perfect grounds for transmission of, yeah. Anyways, she also learns that 5 of the cases were in a group of 7 students in the classroom who were responsible for taking care of a classroom turtle. Which activity is most likely the source of the illness, the assembly or the turtle care? And the question asks you to explain your answer from an epidemiologic perspective, i.e. populations and likelihood, not from a microbiological perspective, which would you point to the salmonella coming from the turtles. But from an epidemiological perspective, it's kind of almost more clear, because all of the 5 cases were exposed to the turtle, where 0 of the there are 0 cases amongst those who are not exposed to the turtle. And in contrast, while 5 of the cases were at the assembly, so were the other, well, actually, 120 other students were also there, and they did not get ill. So it's more about that exposure and the specificity of the exposures that kind of lead you to a hypothesis. And to test this, you could do a case control study and calculate the odds ratios or risk ratios for the exposures that you're suspecting might have a role in the transmission. And then you can compare the confidence intervals of attack rates between the exposed and non-exposed, as we did with that previous question. And that would give you some statistical evidence that your exposure that you were considering was actually was associated with the infection or the illness. Okay, so here's a more advanced example from a clinical setting. Let's say that you have a hospital A, and the HAI rate in the inpatient population of 1 unit was high in comparison to other units in this large referral facility. And this particular unit has many oncology patients. Now, if you wanted to devise a hypothesis or test or investigate this question, how would you test the hypothesis that the oncology patients are at higher risk of HAI than non-oncology patients? So would you, for example, test to see if the proportion of oncology patients is higher in this unit than in the rest of the hospital? Well, that might be helpful for some people to know, but it's not necessarily testing the hypothesis that you have at hand. So this is an example of where it's really important to understand what is the objective of your question or your investigation, and really honing in on exactly what the question is and how to test for it. So, could you compare the HAI rates amongst the Hospital A's oncology patients to the rate amongst all other patients? Sure, that would be exactly what is going to test the hypothesis that's written in the question. So you could compare the 95% confidence intervals for oncology patients and non-oncology patients, and to see if that confidence intervals do not overlap, then you've got a statistically higher rate, or I'm assuming it's going to be higher, but or you can calculate an odds ratio or risk ratio, and that doesn't in and of itself, the calculation of an odds ratio and a risk ratio actually test if it's statistically different, but it does quantify the magnitude of the risk. So with the tools that you have, you would still need to, you may be able to give a risk ratio, but you would still need to have another test like the confidence interval test to see if there was if this risk is statistically significant. And then my last little point here, does this explain why the unit has had a higher HAI rate? Not really, and you may have to do more advanced analysis to explain it, but it's certainly a good, strong starting point. And that's it. Thank you very much.